glyph rendering.
Thank you. Thanks for making time to be in this room instead of the big one. This is the end of the day, I know. I only have 150 slides to go, so feel free to interrupt. OK, how to get your CFP accepted, a case study. So it helps if your project is established, has millions of users, has changed the world, it has a community around it, many high-profile users, and it's booming. Fail. If it's experimental, unused, will change the world in the future, no community, no users, and hasn't been touched in over a year, you will get access. So, next part, submit. For those of us from the other hemisphere, most of the time the CFP ends while we are in the middle of GRADAC, tricky. So make sure you submit. And how to keynote LCA? I was going to ask Matthew Garrett. Oh. OK, so GLyphy, an experiment in GPU-accelerated text rendering with GL ES2. So how do we render text right now? Basically, what we do is we modify these glyph shapes on the CPU for their transformation and font size. We rasterize it on the CPU, upload to a GPU texture, and play. The problem is, if you want to change the font size, you have to redo this again. So if you have animated text, you have to re-rasterize every glyph, every frame, upload it, render it, next frame. So let's do something better.
Hey, that's mean. You show that font again, I'll call me
So the problem is many smart people have spent like 20, 30 years thinking about this problem. So if they couldn't solve it, why do you think I can? So something had to give, and we figured, let's figure out what we can do better on high-resolution displays. So when we started, we were thinking about 200 plus, maybe even 160. These days, the phone in my pocket has 445 DPI, so let's say 300 plus. So this is what we get from the font, an outline in Beziers, second degree or third degree Beziers, and our job is to transform these into pixels on the display. Now, what we have been doing for the past 30 years, everyone does on the CPU, is what we call coverage-based antialiasing. So basically, you draw the pixel on the shape, see what percentage of the pixel is covered, and you assign a number, a shade of gray based on that coverage. The problem is, again, you can only do it for the same transformation. So there's this other thing, SDF-based anti-aliasing, and I get to SDF in a second. The idea is, imagine the pixel is a Gaussian, it's just a hollow. Now,
which they used to be.
Yeah, exactly. They used to be on the old displays. Now, with new displays, they actually are rectangle, but we are moving to this model now. But hold on a second, we get to that. Remember, we have 300 DPI. And if OLPC and Pentile could get away with rendering to those funky pixels that no one noticed, we're good. So now, if you have this pixel that is round and circular, and if you can find the distance to the outline, and this distance is signed, meaning it's positive if you're outside, it's negative if you're inside, then you can just assign a number based on the distance. That's signed distance field-based rasterization. Yes. So this is the signed distance field of the glyph. It's positive on the outside, negative on the inside. You pass it through a smooth function, you get your anti-alias rendering, right? The nice thing about this is you can make it blurrier or sharper. Shift it to get bolder or lighter. So
don't do that again.
I know, but you can.
Basically, you should.
Right. So the kind of smooth function you use changes the kind of anti-aliasing you get. The first top one assumes a perfectly rectangular pixel, and you're scanning a line to the pixel. The second one is the smooth step function of OpenGL. It's basically second-degree continuous, but not at the corners. The third one is second-degree continuous all over. And the last one is the curve you get if your pixel is exactly 45% rotated. So even if you assume a pixel that is rectangular or square, you can mix between the first and last depending on the angle of the pixel. This is what I do, but makes no difference, really. You can't see the difference. So the nice thing about SDF is it is linear over uniform scaling and translation. So if you represent your SDF once, it's just linear math to scale and move the image. Now the problem becomes how to represent this SDF on the GPU. Now what problem have, so normally what people do, rasterize to a texture. This is kind of a rasterization, upload it and bleed it. So when they want to use the SDF, they put the SDF on the texture. So you sample the SDF, put it in a texture, on the shader, you bilinear interpolate the SDF. The problem is, again, when you zoom in, you get the same usual sampling effects. You lose sharp corners, you get bumps. It just looks bad. But game developers love it. So let's vector all the, I don't know if vector is a word, but so we want to put actual vector data on the GPU. So the problem, computing distance to Bezier is hard, really hard. Like for a third-degree Bezier, you have to solve a fifth-degree polynomial. Now again, like any other computer geometry problem, Jim Blin has a solution to it. There's a heuristic, but even that is too complicated, too complex, too heavy. So what we do instead is, ouch. So what you can do, convert to line segments. That's what we do on the CPU. It works fine, but the problem is you get this kind of thing again. So the alternative I want to pursue is convert to circular arc splines. They look much better. So now we have a glyph, which is a Bezier spline. We want to convert it to an arc spline approximation, right? So first we need an error function. So this is your, say, curve, a circular arc you want to fit, and now I want to know how bad that is. So that I developed. Then I developed a physics simulation model to use as many arcs as necessary to achieve a certain tolerance. So this is kind of what you get, a bunch of arcs. And looks much better. This is all arcs. The number of arcs you get is about maybe 50% more than the Bezier, which is amazing. So GPU time. So stuff it all on the texture, ship it on the GPU for every pixel, find the closest arc. It worked. First time I presented this, it was running at 3 frames per second, and each glyph took 50K of GPU memory. And, and I said, OK, I only need to make it 20 times better. And people asked me, the first question after the talk was, do you think you can do it? So people thought I was insane. So yeah, you're insane. So there's a lot of overlap, corner cases to get those to just show up. There's like overlapping contours. If the two arcs are tangent, you can mess them up. They can cross each other. The float precision on the GPU. So yeah. So now what we want to do is to have fast random access to the closest arc. So what we do is we put a coarse glyph on the coarse mesh on the glyph. For each item, we just care about the arcs that may be closest arc to some point in this grid cell, and then various optimizations. So again, this is the line with the arcs, and the shade of gray here shows the number of arcs that may be closest here that we care about. So it's 1 most of the time, it's 2 sometimes. So this is a glyph. The green shade shows the number of arcs we care about. So you see around here, there's so many arcs that may be closest. In fact, no matter how fine you go, there are points that are closest to many arcs. But the nice thing about it is pixels are so small, we don't really care if something is 20 pixels away. So for these areas, we can just throw them away like this. So for this area, we don't care. It's just too far. Well, here, this is too far away from any arc. We don't care. So the shade here shows the number of arcs we care about. Here you see it's most, it's like 2 here, 3. And here you see one of the optimization. If the closest arc is, there's only 1 arc and it's a line, we store it very efficiently. So you get the glyph again, and now the rhetoric changes. It's insane. So demo time.
Who is that?
I don't know. You changed your shirt today. Okay, this is my system monitor. There's 4 cores, they still keep working, but glyphy demo, well, let's make it a bit bigger. So we still can see this. Okay, so this is like every single pixel, every frame is being rendered on the GPU, nothing on the CPU. The only thing the CPU does at every frame is, if you're animating, just change the uniform to set the matrix. So I can move it around. If I'm lucky, I can zoom it. Oh, I'm not lucky. Yeah, I can zoom it infinitely.
Moving further. Keep going. Keep going.
Let me bring an R.
Find the round letter.
Yeah, that's what I'm trying to do. Okay, you kind of see some artifact here. Okay, you proved your case. But no, the artifacts don't blow away. So this is the debug info. You see the distance field, the number of closest arcs, the arcs themselves. You know, I don't know why the gamma correction is really bad. Anyway, so, and if we go back here,
Some discontinuities in the connections between circles and lines.
that may be the glyph shape.
Yeah, it could be. I'm looking at the top of the right stem of the H.
Here?
No, the right stem.
Okay, like here, right?
To make the glyph line up properly, you'll just be taken up in the antialiasing.
Yeah, there's,
There's a discontinuity
yeah.
at the top of
That's just bits. I store X and Y using 12 bits. And then the arc and line use different storage, so the line and arc don't line up. Okay, so back, zoom a bit, and the nice thing is you can have projective transformations.
Because everybody needs that.
Okay, and the thing to notice is there's nothing happening in the CPU. Okay, so I'm getting ahead of myself, but so the nice, as I said, this is the SDF is invariant over a uniform scale, but if I scale it, how do I do that? Okay, yeah, you see the anti-aliasing on the x-axis is just too much. We have a fix for that. So, and if we see what kind of frame per second we are getting. Yeah, something is capping it at 60. I don't know what exactly. It can go faster, I'm sure.
Well, you just need to run it with feedback coding from 0.
I have, but it doesn't help. That's the GLX thing. No, same thing. I used to get before GNOME shell and stuff.
Oh, GNOME shell. You need to turn GNOME shell on.
Yeah. So what else can we do? Well, okay, you said don't do it again, but, and of course we can get a, oops, no. And can get outline for free. Okay, I think that's all I have. Gamma adjustment, contrast, all those things I can change.
Ooh, that's fun.
Gamma, let's see, it's, yeah. Oops. Yeah, good luck finding the right value. What's that?
And when you went very thin, suddenly the H got very active.
Yeah. Well, he's changing the gamma function here.
Yeah.
He's not changing the thickness. Oh.
Yeah. Okay, that's all it can do, basically. Back to work. Okay, limitations. Main thing, memory. So now I've got it down to over about like 2K per glyph or better.
That's not bad.
No, and
If you think about the size of an image, it's at least 4K.
I know I'm going there. And so I've got it under 2K and about 2 point something texture fetches per pixel. And now, if you have a single letter I or G, it's 8 pixels by 16 on your normal display, that's only 100 bytes. But on this phone in my pocket, that takes 20 times more storage. So that's like 200K for one rendering, one size only. So I'm already way ahead of like if you have a couple sizes. The problem is speed and memory are font dependent on every pixel, every frame. So font complexity is carried along onto every frame. So you say, yeah, if you have something like this, this one actually works. It's not much worse. But, no, that's something museo or something. But the problem is people do this. That's over 100 times more complex than your normal font. And when I try to render this one, the way I'm storing my stuff in a texture, I have a big texture, use it as an atlas with a width of like, I take 64 pixels wide and go down. This one needs to allocate more than a whole column. So I don't wrap and it just doesn't work. Advantages, memory footprint, as I said. So subpixel positioning is for free. Every pixel, every frame is subpixel positioned. Pinch to zoom is just normal. That's what this is designed for. So challenges. Talking to you, Eric. So shader size complexity. When I started this, people were like, you're crazy. There's no way. Shaders are not for this. Pixel cost. Again, when I was talking to one of the Android people 2 years back, they were interested. They said on Tegra, on some Tegra, we can afford, to get 60 frames per second, we can afford 1 texture fetch, 1 multiply, 4 adds. And I'm like, OK, I need 3 or 4 texture and 100 times the operations. Dependent texture lookups, again, people say it doesn't work, you can't do on ES2. So I need to look up something. Based on that, go look up some other things. That's how my grid works. So the first entry into the fragment shader, I see where in the grid this is, get it, go fetch the arcs, go through the arcs, right? So variable loop iterations, it told me like the loop has to have a fixed number of iterations. So fine, I cap it at 32, I break out of it. And interpolation accuracy, that's a more problematic one. So if I have variance passing from the fragment shader, the vertex shader to the fragment shader, and I'm using this for integer things, right? Those are like array indices and stuff. Looks like as soon as you have a projective matrix, like even if the variant is the same on all the corners, you lose 1 or 2 bits during the interpolation. So just don't use the lower 2 bits. So this is what people used to call a complex fragment shader. And it's cool. It renders this. So mine starts this way, like any good open source software. This is so this is a shader library. So you include the shader in your code and use it. So this is like the integration point. You define macros to integrate. This is how I access something. You define this to access your texture. This is my main SDF. This part is only the optimization. If it's a single line, if it's not close to anything, I handle it. Then I get ready for the actual for loop over the arcs. And this is the for loop, only, again, this is the optimization part. The actual going through every arc. This is the easy case, and this is the corner case. And finally, you just return the main distance signed. And it renders this, right? So drivers. Can of worm doesn't start it. OK, case study. Meta software render actually used to render this at some point. And then it started saying infinite loop detected in fragment shader. And Eric said, just forget about it. I'm not going there. NVIDIA on Mac has been so far the best driver for this, fastest. But again, every driver combination, every driver and operating system combination, we had to bring this up. I never got this bring up idea until I got here. For every single driver, we had to change things. And it's not like we were doing something bad. The driver was so broken. So in this case, apparently the shader compiler doesn't like token pasting. So I used to have token pasting so you could namespace my function in your shader, so I removed it. 150 plus frames on MacBook Air 2011. On a Retina, it goes about 30, so needs some speed up there. AMD and Mac. Oh, the AMD compiler was even funnier. So this code here, was never getting wrong. Just moving it into a function fixed it. I don't know. Intel Linux, yeah, oh yeah. It used to just refuse to compile the driver, saying failed to spill registers. So Eric was nice enough to spend a lot of time and got this commit in. Do you want to explain?
No, I really don't want to working on that.
Basically, what was happening, if you had a loop, every variable access in the loop was allocated registers and retained for the entire life of the loop. So he just implemented some very basic compiler optimization things. And it's working. It's been working. Yeah, it was so hard, I had to keep one version of good Mesa around. So it runs 60 plus. I'm sure it goes faster. It's just my GNOME shell. It's a 2-year-old ThinkPad and stock Ubuntu 12 something, 12.4. Again, full HD display. iPad 3G, someone got it running on there. It's like, run slow, 3 frames per second. I still want to see it on 5C or 5S. So Android 4.3, oh, driver bike. So the red lines of code used to correctly return 1. If I used an intermediate variable, it was returning 0. There was just no hope for this one. Fortunately, I just had to wait. 4.4 fixed that. So, well, I still needed a single patch. Like, this space here was if the space is there, the macro is not expanded. So, easy fix. And it's been running 25 frames per second on Nexus 4 and 5 at full HD resolution. I have it here if you want to walk over and test it. It also runs on the Nexus 12 2013. So the code is in libglyphy, is C++ with a C header, like 2,500 lines of code, 300 lines of shader, no dependencies whatsoever, no OpenGL, no FreeType. You feed it the outline, it gives you a blob that you are supposed to take to the texture, and then you get a shader source, you integrate it in your own shader and push it out. So the glyphy demo is about 300 lines of code. That's accessing the font, laying out, then getting the blobs, putting an add class, uploading, and using Cloud to drive the interactions. So subpixel rendering, we actually have it done. It's not much more complicated. So you just need to change your SDF to, instead of just returning the distance, return the vector, the direction to the closest arc. And then you have the direction, you have 3 subpixels, you approximate the distance of each of the subpixel centers. So it's not 3 times the cost even. Anisotropic antialiasing, again, we have something close to it. It's not complete. The problem is a circle, if you stretch it, it's not a circle anymore, right? And on the other hand, or the other way, the way we calculate the distance to the circle is we calculate the distance to the center minus the radius, right? That just doesn't work for an ellipse. So, but again, what we can do, we can get a vector to the arc, and then when we are dot producting that with the pixel dimensions, the pixel now has different dimensions in different directions. So you can kind of approximate that. So that's the main part. Now I'm going to, maybe I was insane because I'm going to show you what we had to go through to actually get this to work. And we are good in time. I can go through this in 5 minutes, I think. So this is a letter. This is the SDF. That's with the parts removed, parts that we don't care about removed. So this is a very coarse grid. I can go finer and finer, throw some away, even finer. So you still have those bright spots. So this is the SDF. This is the DF, distance field. I get the sign. Now, if you're not careful, you can mess up things. So if you have a point that is closest to 2 arc corners, now figuring out whether you're in or out can be tricky. So that was the first problem we had to solve. There's like tons of we had to solve 20 different issues to get it to work. So if you're not careful, all kind of crazy things happen. If you are careful, still some other crazy. This one actually is a font bug. The font has 2 points very, very close, which should actually be 1 point only. So, oh yeah, this is interesting. So if I was to just use the SDF, this is the SDF, it's around here, right? But we have a mode to do something called pseudo SDF, which produces these sharp corners. I'm not going to say what that's useful for, but emboldening. Okay, so again, artifacts. This is, if I remember correctly, float precision issues. If you're calculating the arcs, intersection, those things can go bad. More. Okay, now it starts getting funny, because you can get so close to being right, and then this one arc is totally wrong. So even this, okay, this is like, you see the discontinuity here. All kind of fun. Oh, this one again, see, it's almost right, but you get these two like flip. All kind of crazy things. I call this the spooky G. All over, like this 1 point happened to overflow, I think. Yeah, it was outside the bound of something, overflowed. Like all over, every one of these, like me or my intern had to spend days to figure out. And it's the GPU, you don't have printf, right? This is the Voronoi of the G, actually. Okay, and this is the patchy G. And that's all I have. Questions? And we have about almost 20 minutes. Go ahead.
Do you handle kerning in there?
Do we handle kerning? Yeah, so this is the thing. We don't do hinting, and you shouldn't really want hinting. But everything else, ligatures, kerning, funky contextual things, those belong to the layout layer. So layout is Harfbot, my other project. So you give the text and font to Harfbot. It says, render this glyph index here. And that's when the rasterization starts. So these are completely separate things. So yeah, we do that. Go ahead, yeah.
Have you done any benchmarking in the other direction of a benchmark that keeps adding glyphs until you drop below 60 frames so you can get a measure of glyphs can I do 60 frames?
So the question is if we have done more benchmarking, see how much we can put on it. So good question. The thing is, like, the main work on this ended a year and a half ago. The problem at that point was there was no target for this to work specifically on making it fast or measure things. Because I don't see like the Linux desktop using it. Well, maybe with Wayland somehow. But it doesn't fit in the Cairo model, the Pango model, the GNOME model, GitK model. And like the mobile GPUs were just not there. But now it's starting to get interesting because it looks like mobile may be able to use it. Now, NVIDIA has released a demo or prototype of a mobile GPU that is faster or as fast as desktop. So it looks like 2 years from now, it may totally be running Android. So when we have that kind of target that I now have in Nexus 5, I can go measure things, see if it's the texture fetch that is causing the main blocking, or is it operations or texture memory? So no, I haven't done, but this is something I look myself as spending a good part of 2014 on this. Go ahead.
Have you looked into using GLSL optimizer to feed optimized shaders to the mobile drivers?
Interesting. So the question is if I've used shader optimizer to pass this through. No. Is there anything other than Angular?
So it was the creator of Unity took Mesa's GLSL compiler and built a little driver backend that emitted GLSL code. So he just took his shaders that his infrastructure was generating, ran it through Mesa, pulled GLSL code out the other side, and got huge performance wins on iOS.
So I should.
And he's still using it in his pipeline.
I should talk to you about it.
These mobile driver
Awesome.
compilers just.
The other thing. Yeah, go ahead. I forgot.
Yeah, finished. Okay.
No, I forgot.
So I have one other observation that's not really a question. All of these graphs that you're doing look suspiciously like the
Yeah, a lot of the comment was that a lot of this looks like what you do in 3D printing or other geometry. Yeah, I think arcs are very relevant to whatever physical movements you have.
In terms of, I could take this and I could make Rec Snapper do your
Cool.
3D
Yeah.
printing slicing on the
Yeah. So I've got to say the main idea of using arcs this way was not mine. It was from a PhD thesis of someone at U Waterloo, and they were looking into these things for generic curve rendering or SVG rendering on the GPU. And the problem with a lot of this is if you have detailed like images or sharp corners, a lot of this doesn't work. But for glyphs, it's much more well behaved.
Yeah, I guess that's the other problem. You've got a constrained size with a glyph.
Yeah.
The generic object you want to print.
Yeah, and you have like one colored image at a time. You don't have a full SVG with gradients and stuff. But
So if you do like creep the text by less than a pixel, quite often you see flashing when you render. How does?
So,
I'm
yeah.
sure you can do that in your test program. Is it actually smooth and you don't see dark?
right, so the question is if we have a slow movement, does it jump or is it better? That problem, as you say on Cairo, for example, which is in GNOME. I know you don't use GNOME. So Cairo's Cairo's raster backends don't do subpixel positioning, so they just round the pixel, the image to a pixel boundary. So subpixel positioning is what we call being able to render raster differently based on your and this is fully subpixel position. So
right, but does it actually? So what
if
often happens when you do subpixel is that depending on where letters end up, it doesn't actually.
Look
Sometimes
right.
they look darker, sometimes they look.
right,
bright.
that's your gamma correction.
Yeah, you need to get, the problem is if you use a linear gradient for the colors, the problem is your display is gamma. And so you actually need this gamma filter
Yeah.
on the anti-aliasing.
And
And
are
this
you doing
does
that
that.
correctly?
Yes.
So.
Can
So-
you show us?
So I think so this is at the end. So I'm showing black and white. It's easy, but to do it correctly, you need to blend in a linear space. And there's a GL extension for that, right? For sRGB.
Yeah.
If you don't turn that on, you still can't get the full thing. Because like to do it really correctly, what you want is you have your source value, get the destination, convert this into a linear space, blend, and convert it back. Can I show it? I don't know how exactly to show that.
It actually usually works better with small text.
Yeah.
Shift slowly. I don't know.
I'm trying to see if I can. It's probably hard to. I mean, the mouse.
There's more flickering from
yeah.
repainting.
Yeah. The mouse coordinates I'm getting in the demo is like pixel, whole pixel. So I look into it. I haven't produced demos for that. I know other people have looked into it using this to render very thin slope lines at subpixel positions. Yeah, that's something I need to produce more demos of. Go ahead. The code for the demo. Oops. It's not really that interesting. That's okay. That's the other thing. I once managed to, with some version of mscripten, to compile this using mscripten to JavaScript and WebGL. It used to run just fine. So the main problem, for example, on Android, it takes maybe a couple seconds to come up. That's the shader compilation. That's the slowest part. So the
was 3.txt.
what?
So it was 3.txt. You're all set up for the intros.
Yeah. So this is like the main driver, just calling glot to set things up. What I have here is, well, I have a font abstraction, so that just basically you ask for a glyph, it gets a glyph from FreeType, feeds it into GLyphy. GLyphy. Yeah, this is the main part. So basically, you feed the arcs into the the Bezier into the arc accumulator, then you get this function. It takes the arcs and codes it into a binary block that you then need to get to the GPU. Then I have a atlas, a very trivial one, basically. So I just keep, for every glyph, I know this rectangle in the texture is the binary block for this glyph. So for every glyph, I just produce 2 rectangles, like 6 points, and assign the texture coordinates for it. I also, there's a 16-bit number that comes from the glyph. I need to pass that through to the vertex shader. I mean, that saves one texture fetch. So then my V shader, oops. So this is my V shader. Basically, it takes a matrix, the glyph vertex. So what does it do? Okay, so it gets a glyph vertex info that has the corner. It says like x0, x1, y0, 1, y1. And then, as I said, a certain number that is per glyph fixed, I need to wire it through. And then it gets the position like you do like in every shader, and then transcodes the data for the fragment shader. And then I have the atlas. This is the integration part with the library. This is the function that I give it, like, I use the 2D texture as a one-directional array, right? So I say, okay, I want this point in the array, and this integrates it into my atlas. And well, GL3 has a 1D array and those things, but we don't have here.
Have you looked into porting to desktop GL? I mean, there's a bunch of stuff you're doing here that's workarounds for.
Yeah, it runs on desktop, but it doesn't use GL3 specific thing.
Texture buffer objects, it looks like you wanted there. Your attributes look like you had a flat attribute that you had troubles with interpolation.
Yep.
Just use the flat. Oh,
I know.
you don't have the flat
Well,
modifier.
that's not even in GL2, right?
Flat was GLSO 130, yeah, so GL 330.
Right. I don't even have GL3.
I don't know, GL3.
Well, because I don't see any target on desktop for this. If someone wants to use it, like if you have a platform that can plug this in, I totally look into it. But as I said, your general desktop, there are other people using it in STL based or those kind of scene graph things.
The question is, it's very much, it doesn't seem like it's environment specific. It's very application specific for applications that are doing massive text animations.
Right. So yeah, my question is, what are some good applications of this on the desktop? And the fragment shader. So basically, these are the uniforms control all the bold outline debug stuff. So, and this decodes the stuff that the vShader encoded for us. And these are the anti-aliasing functions. Now, you notice I'm actually doing the square pixel here. So this is the axis align, this is the diagonal, and then it interpolates based on the direction of the pixel. Yeah, I should remove it. I don't know why I have it here. And this is the main. The main is basically, yeah, this much. So I decode the stuff, get my pixel size. This gives me the pixel size, right? And I get the distance from glyphy, and well, apply boldness, anti-alias it, adjust gamma, and just return. That's it. Now the debug mode, all those fancy colors, that's what's here. So that's the demo. We have 5 minutes left. If there's
One question.
Go ahead.
How do you handle things like
Arabic or Debugging with indicated glyphs?
So the question is, how do we handle complex text like Arabic Devanagari? It's a shame because I develop Harfbot that does that on your phone, Firefox, Chrome, GNOME, but oops. Let me see. Files.
When you're running it, you're trying to get above 60 FPS. You try turning the blank code to 0.
1 second. So no, it doesn't work right now because I haven't hooked up to Harfbot. But again, that's a shaping layout problem. It's on top of, like, before we get to glyphing. I should do it. I know. Go ahead.
Embarrassing enough to be able to display
If
for
you prefix your command with v_blank_mode equals to 0, you might be able to get above 60 FPS. Are you happy?
I am.
The problem is it's running GNOME shell.
Yeah.
Oh, okay.
Yeah. Tonight I'll look into that. I can probably boot into, like, logging into the old GNOME 2 compat player. Okay. Any final comments or questions? Nope.
It still looks crazy.
Thank you.
I think it's kind of crazy.
Go ahead.
VC normally be like
Will you be releasing the code to get your bat shapes? To make the text look like bat shapes that you had from G?
Oh, so do I release the code to detect the bat shapes, or?
You know how with one of your genes, it could flip all of your
Yeah.
Will you be releasing that code?
Oh, yeah. You know, that code is in my Git history. I used to, when I was, like, the gallery images just are images I saved over a year and a half. And at some point I was tagging individual commits with, like, this is that image. But I stopped doing that. It was just so much stuff. But, like, there's a date range. Any commit you check out has those psychedelic images. Okay. Thanks all. I can go drinking now.
Yes.
Bye.